In the previous exercise, we have shown the following. The set given by the n tuples in Rn satisfying the following linear homogeneous equation, summation for I that goes from 1 to n of lambda I times xi equals to 0. This is just a generic linear combination of xi times lambda I for lambda I fixed coefficients. So a homogeneous linear equation equals to 0. This is, in fact, a subvector space of Rn. Now we are going to prove a generalization of this statement, and we will consider the set B given by n tuples in Rn, satisfying not only one linear equation, but k of them. Okay, we will denote by lambda ij the coefficients of the linear equations here, and the first index will indicate the linear equation, and the second coefficient will be running through the summand of the linear equation itself. The statement we will show is that this more general set B is going to be a subvector space of Rn, just like it was A. So we recover the case A just considering one linear equation instead of k of them. There is a fundamental remark that I would like to do at this point. Any set B of this form is going to be a subvector space. But in fact, any subvector space of Rn is going to be of this kind. Okay? So we cannot prove it now. We will be proving it after a few theoretical results will be shown in the theoretical lectures. But be aware that now we are not restricting to some particular subvector space, but we are just treating them in the broadest generality. So any subvector space of Rn can be written like so. So to prove that B is a subvector space of Rn, can use two arguments. The first one just shows that the intersection of two subvector spaces, and actually this is true for any vector space V. We are not going to be using the fact that V is Rn, the Euclidean n-dimensional vector space over R. So it is always true that two subvector spaces, their intersection is also a subvector space. Now, if we knew that, we will right away deduce that B is a subvector space of Rn. Why? Because B is precisely given by the k-tuple intersection of k subvector spaces of Rn of the form A. Just for example, consider B given by two linear equations instead of k. Now, the set B of n tuples satisfying the first linear equation and the second linear equation simultaneously is precisely given by the intersection of the set of n tuples satisfying the first linear equation intersected with the set of n tuples satisfying just the second linear equation. And if we know that the intersection of any two subvector spaces is still a subvector space, then we conclude right away that B is a subvector space of Rn. Now recursively, we can right away see that the k-tuple intersection of subvector spaces will also be a subvector space of Rn. So this would imply, one would imply that B is a subvector space of Rn at once. We are not going to follow this path. We are going to use another argument. In the lecture 6.5, where we have stated the RC theorem regarding set of solutions of systems of linear equations. Why is that? So if you look carefully at B, B is precisely the set of solutions of a system of linear equation, homogeneous system of linear equations. You see, here all these k linear conditions on the xi's constitute a system of linear equations. Therefore, we know that the set of solutions of a system of linear equations is not going to be a subvector space over n. But in the case the system of linear equation is homogeneous, then we already know that the set of solutions is going to be a subvector space. Okay, so just quoting RC theorem, a part of it, we will know that this is a vector space over n, but RC theorem tells us more about this. Tells even something about the dimension of B. B being a subvector space over n will have an associated dimension, and if we just look at the statement of the RC theorem, we will deduce the following. So the dimension of B as a subvector space is going to be equal to n. N in this case is the dimension of the Euclidean vector space, and also the same as the number of unknowns here, which are of course the coefficients of our vector in Rn. So n minus the rank of the associated matrix, whether it be the incomplete or the complete does not make any difference in this case, because we already know that there is a solution. Homogeneous systems of linear equations always have a solution, namely the zero solution. So we don't really have to check whether the ranks of the incomplete and the complete matrix coincide. They always coincide because the complete associated matrix will be just the incomplete with a zero vector added as the last column, which of course will not change the rank of the incomplete matrix. So the condition of the equality of ranks is always satisfied in a homogeneous system of linear equations. What we actually have that is usually a non-trivial information, precisely this, that the dimension of B of the vector space of the solutions equals n minus the rank of the incomplete or complete matrix. This shows that this is a vector space of this precise dimension. In the next exercise, we will see how to find a basis for this subvector space, an explicit basis.